Thank you for joining us today. I'm Jeannie Harshaw, and on today's Engineers Newsletter Live program, we'll be discussing Airside and Waterside Economizers. But before I walk through the agenda, it might be best to review what an economizer is. The use of an airside economizer allows the system to provide cool outdoor air to offset space loads, which reduces and sometimes eliminates the need for mechanical cooling. Conversely, a waterside economizer cools a fluid such as the condenser water or chilled water using a heat rejection device without mechanical refrigeration. This fluid is then used to cool the supply air. In general, airside economizing is more beneficial than waterside, and choosing one doesn't preclude the other. Designers can choose to use both types, even at the same time. So in today's program, we'll start by reviewing economizer requirements found in ASHRAE Standard 90.1. Then we'll look at individual advantages, drawbacks, and considerations for airside and waterside economizers. And finally, we'll discuss some system type variations. To walk us through the discussion, we have Trane application engineers Susanna Hansen, Dustin Meredith, and Eric Sturm. So Eric, can you start us off with the requirements of Standard 90.1?
Sure, Jeannie. Standard 90.1 is on a 3-year continuous maintenance cycle, which means it's updated and published every 3 years. And there have been some significant economizer requirement changes in the past decade. Today, I'm going to talk about the requirements from the 4 most recent versions: 2007, 2010, 2013, and 2016. Why 4? Because those 4 versions are in common use today. Now, all have prescriptive requirements about economizing, and none stipulate whether a system should use airside or waterside economizing, except in one instance where humidification is being performed. And because these are prescriptive requirements, there's at least one other path for compliance, such as the energy cost budget. I'm going to use this key in the upper right of the screen to specify which versions the content on the slide specifically relate to. If the year is grayed out, know that it's not applicable to that version. So let's start with the requirement to economize. All 4 publications start the prescriptive requirements section with economizers. The introduction is virtually the same across the 4 publications. Here, the standard says that each cooling system shall have an airside or waterside economizer complying with additional requirements. Remember, the standard does not say which to use. That decision is left to the designer. Now, the requirement does include a variety of exceptions, and those do vary between the versions of 90.1. The first exception provides a minimum system capacity for economizers. Here's a climate zone map of the continental United States. Climate zone assignments are shown in Appendix B, which also includes locations outside of the U.S. The 2007 publication provides climate zone specific minimums. The exception says that units smaller than a specific capacity are exempt from the economizer requirement. In general, hot and moist climates are exempted from the requirement. Climate zones 1A through 4A and 1B, hot and dry. You can see these in the continental U.S. map in green. For milder to cold climates, climate zones 2B and 5A through 8, economizers are required when the system capacity exceeds 135 MBH, or about 11.3 tons. Finally, warm, dry, and marine climate zones require economizers when the system capacity exceeds 65 MBH, or about 5.4 tons. In the 2010 publication, the committee significantly changed economizer requirements. This included the climate zone specific requirements. The map and size thresholds are the same in the 2013 version. For comfort cooling applications, installations in climate zone 1A and 1B are exempt. All other systems greater than 54 MBH, 4.5 tons, are required to have an economizer. So with this change, a greater number of systems will have economizers due to the increase in climate zones and the lowering of the threshold from 11.3 or 5.4 tons to 4.5 tons. Now, there are separate minimum capacity requirements for units that serve computer rooms, but we're not going to focus on those today. Today we're going to spend our time on comfort cooling. For 2016, the minimum capacity threshold at 4.5 tons did not change. What did change, however, was the climate zone map itself. In this version, Standard 90.1 now references the climate zone maps published under ASHRAE Standard 169-2013, Climatic Data for Building Design Standards. This new map also includes new climate zone designations, 0 for extremely hot, with A for humid and B for dry. The size exception is similar. Units smaller than 4.5 tons and those installed in climate zones 0A, 0B, 1A, and 1B are exempt from the economizer requirement. Looking back at the map, you'll notice several counties in the very southern part of Texas are now in climate zone 1A, meaning they're now exempt. This map shows which climate zone assignments have changed in the 2013 publication of Standard 169. Counties marked in red have been redesignated into warmer zones, while those in green have been redesignated into colder zones. Again, those southern counties in Texas moved into 1A, so they're shown here in red. Now, what we just discussed was the first exception, which deals with cooling capacities and installation locations. There are other exceptions to get out of the economizer requirement. In 2016, we had an extensive program called Delivering Performance from Airside Economizers, and in it, we discussed many of these other exceptions. That program is listed in your bibliography. A new exception was added in 2016 to specifically address chilled water cooling systems that do not use fans or have induced airflow, like chilled beams. The exception states that systems with a total capacity less than 1 million BTUs, or about 83.3 tons, installed in climate zones 1B, 2, 3, and 4 are exempt from the economizer requirement. And if installed in climate zones 5, 6, 7, or 8, the economizer requirement is exempt if the system capacity is less than 1.4 million BTUs, or about 116.7 tons. As before, if the installation is in climate zone 1A, chilled water cooling systems that use induced airflow or do not have a fan are exempt from the economizer requirement. All 4 versions we're discussing today include an exception to get out of the economizer requirement if unit cooling efficiency is increased by a certain amount. The language shown on the screen is from 90.1 2016. The exception cites a specific table of energy efficiency improvements, and that reference table number does vary by standard version. This allows designers to increase HVAC unit efficiency beyond the minimum required value and eliminate the economizer requirement. The efficiency threshold is climate zone dependent, meaning those climates where economizers can do the most good, reducing the mechanical cooling run hours, have the most improved thresholds. Now here's what the table looks like in the 2007 version. The table is divided into 2 halves: unitary systems with heat pump heating at the top and other unitary systems at the bottom. System sizes are shown along with the mandatory minimum EER value. Then the climate zone dependent minimum cooling efficiency required EER. Notice for either type of system, no improvements are listed for climate zones 5 through 8. Within the table footnotes, it states that economizer elimination in these climate zones is not allowed. Consider an example installation of a 20-ton rooftop with natural gas heat installed in New Orleans, Louisiana, climate zone 2A. According to the table, the EER must be increased to 10.3 to eliminate the economizer. For the other 3 versions, the table has climate zone specific efficiency improvement values. From the table you can see that the climate zones move from hot and humid, 2A, to subarctic in climate zone 8. The percent of efficiency improvement grows. The percent improvements in the cold, very cold, and subarctic climates may be impractical. Consider another example in Baltimore, Maryland, This would be climate zone 4A. If the designer wanted to eliminate the economizer requirement, they would need to increase unit efficiency by 42%. Footnote A beneath the table indicates that units with part load minimum efficiency requirements like IEER, IPLV, or SEER must be increased. If the unit is only rated with a full load metric like EER, then it is increased. This certainly isn't an exhaustive overview of the exceptions to eliminate the economizer requirement. We covered more in our 2016 E&L on economizers. Now, as you go through the versions of 90.1 used in your jurisdiction, be sure to review the exceptions. All 4 versions of Standard 90.1 discuss integrated economizer control and require the economizer system, air or water, to be integrated with the mechanical cooling systems, allowing the system to provide partial cooling with mechanical cooling to offset the entire cooling load. Integrating the economizer operation with mechanical equipment allows more economizer hours, which results in less cooling energy. Newer versions of the standard specifically prohibit controls from false loading the mechanical cooling system to limit or disable the economizer. Hot gas bypass is also limited except for the lowest stage of mechanical cooling. There are some requirements, including a limit on maximum temperature at which the economizer damper can modulate closed to prevent coil freezing, 45 degrees in this case. If a system greater than 65,000 BTUs, or 5.4 tons, which controls cooling capacity based upon occupied space temperature instead of supply air temperature, a minimum number of stages of cooling capacity are required. An example of this would be changeover bypass, like a Veritrac or VVT system. The idea is that in the integrated economizer mode, a single-stage DX unit quickly overcools the space, causing the unit to leave cooling and economizing mode. Finally, DX units that control space temperature by modulating airflow, like single-zone VAV and multiple-zone VAV systems. The reference table shows DX units between 65 and 240 MBH, 5.4 to 20 tons, must have at least 3 mechanical cooling stages, and units above 240 MBH, or above 20 tons, must have at least 4 stages. Another requirement found in all 4 versions requires that economizer controls ensure the building heating energy usage does not increase due to economizer operation. Said another way, the committee wants to ensure that economizers do not overcool the space. Now, there is an exception which allows VAV systems that see zone-level reheat energy usage due to economizing and the resulting supply air temperature. The 2013 and 16 versions do require the designer to use a Waterside Economizer, if one is required, when the system in question uses hydronic cooling with humidification and the inside space humidity levels being kept at a dew point temperature of 35 degrees Fahrenheit or greater. Okay, that completes the general economizer requirements.
So Standard 90.1 prescriptively requires economizers, but it does not specify whether it's an airside or waterside economizer. And the standard provides a variety of exceptions, which allow designers to eliminate the economizer requirement. There are exceptions based upon installation location, climate zone, and there are exceptions that allow designers to increase unit efficiency. There are also many more for unique cases like supermarkets, healthcare, envelope-dominated spaces, and others.
Exactly. So let's now look at the specific requirements for airside economizers. All 4 versions require an airside economizer be designed to modulate the outdoor and return air dampers to provide up to 100% of the design supply airflow as outdoor air to satisfy the cooling load. And all 4 versions limit the maximum allowable damper leakage. The requirement references a table within the standard, which provides maximum damper leakage values based upon climate zone, building height, and damper type. The requirements vary by Standard 90.1 version, so check the specific requirements. The standard also requires a means to relieve excess outdoor air during air economizing to prevent building overpressurization. Finally, The 2013 and 16 versions have new language regarding sensor accuracy. Temperature sensors need to be plus or minus 2 degrees over a range from 40 to 80 degrees Fahrenheit. Enthalpy sensors shall be plus or minus 3 BTUs from 20 to 36 BTUs per pound. And relative humidity sensors must be plus or minus 5% from 20 to 80% relative humidity. The standards use high-limit shutoff controls to prescribe when economizers are shut off in favor of mechanical cooling. In the 2007 version, there are two tables. The first table indicates which control types are allowed or prohibited for specific climate zones. The second table shows the control types by climate and how the control should work. For example, consider an economizer installed with fixed dry bulb temperature control in Put-in-Bay, Ohio, which is in climate zone 5A near Toledo on Lake Erie. Here, the economizer would need to operate until the outdoor air dry bulb temperature exceeds 70 degrees Fahrenheit. In the 2010 publication, the fixed dry bulb temperature control for all other climate zones was removed. In the November 2010 issue of the ASHRAE Journal, Taylor and Chang discussed concerns about sensor inaccuracy and suggested that fixed dry bulb control provides the best combination of energy savings and maintenance with the least risk of sensor error. This helped justify the reintroduction of this fixed dry bulb control in 2013. Finally, in the 2013 and 2016 versions, the control type table was replaced and the cold shutoff temperature at 65 degrees was restored. Fixed dry bulb temperature and differential dry bulb temperature control remain with two new control types: fixed enthalpy with fixed dry bulb control and differential enthalpy with fixed dry bulb temperature control. Consider another example with an economizer being installed in Chatham, Ontario, which is east of Detroit, Michigan. This is also climate zone 5A, but the designer chose to use fixed enthalpy with fixed dry bulb temperature control. This control specifies that economizing must end when the outdoor air enthalpy exceeds 28 BTUs per pound, or when the outdoor air dry bulb temperature exceeds 75 degrees. The differential enthalpy with fixed dry bulb temperature control is used to end economizer operation when the outdoor air enthalpy exceeds the return air enthalpy, or when the outdoor air temperature is above 75 degrees. Let's consider another example in Plattsburgh, New York, climate zone 6A. At a given hour, if the return air condition is 72 degrees and 45% relative humidity, then the enthalpy is approximately 25.5 BTUs per pound. So, whenever the enthalpy is greater than the return air enthalpy, 25.5 BTUs per pound in this example, the mechanical refrigeration system is operating. And whenever the outdoor air temperature exceeds 75 degrees, the mechanical refrigeration system handles the load. Dustin, fault detection and diagnostics have been recently added to the standard. What should we know about those?
In the past 5 or so years, fault detection and diagnostics, often abbreviated FDD, have been added to local codes, model codes, and standards based upon the premise that economizers do fail. For example, California's State Energy Code has required fault detection and diagnostics since 2014. The 2015 version of the International Energy Conservation Code included FDD requirements as well. And now the 2016 version of Standard 90.1 requires them too. Within these codes and standards, fault detection and diagnostics are a mandatory requirement for air, water, and evaporatively cooled air conditioners and heat pumps where an Airside Economizer is installed. The standard requires a handful of permanently installed temperature sensors, including outdoor air, supply air, and return air if utilized for economizer control. The system must have the ability to display the temperature being read by each sensor. The unit controller also needs to indicate operating modes like free cooling available, economizer enabled, compressor enabled, heating enabled, and mixed air low limit cycle active. Finally, the unit controller needs to be capable of manually setting each operating mode to independently test the operation of the compressors, fans, heating system, and economizer. The fault detection system must also be capable of detecting a number of standardized failures and faults. Examples include improper economizer operation, like when the economizer should be running and is not, or vice versa, and dampers that don't modulate properly. If faults are detected, the controller must be capable of reporting them to a system that is accessible by operating and service personnel, or the faults must be displayed on zone sensors.
Now, many jurisdictions use model codes, such as the International Energy Conservation Code, which is published by the International Code Council, to specify minimum building energy performance. And in many cases, using Standard 90.1 qualifies as a compliance path. Jurisdictions can amend model codes, so it's important to review your specific code. The IECC requirements are similar to those published in ASHRAE Standard 90.1, with a few key differences. First, the IECC prescriptively requires an air or waterside economizer, then provides a number of exceptions to eliminate the requirement. Like latest versions of Standard 90.1, individual units less than 54,000 BTUs per hour, or about 4.5 tons, are exempt in other climate zones, but only if they have DX cooling coils. If the units are served by chilled water and outside of climate zone 1A, the total capacity without air economizers must be less than a climate zone dependent threshold. So consider an installation of a chilled water terminal system in Washington, D.C., climate zone 4A. If the chilled water is provided by a water-cooled chiller, the maximum summed capacity of terminals without economizer cannot exceed 60 tons. And if the chilled water is provided by an air-cooled chiller or a district chilled water system, that maximum is slightly higher at 78.3 tons. Another notable difference includes the climate-specific efficiency improvement values needed to eliminate economizers. In Standard 90.1, we saw equipment efficiency improvements from 17 to 77%, depending upon the climate. Only 3 climate zones are allowed to use this exception, and the percentage of improvement is less than the 90.1 options. And in the 2018 IECC, climate zones 2A, 3A, and 4A have been added. Now, some jurisdictions have modified their respective energy codes slightly, while others have made significant changes. The states of Oregon and Washington have both heavily modified the IECC to suit their specific needs. And I'm sure there are other examples where the IECC has been modified for the needs and wishes of the specific jurisdiction it serves. Again, this is why it's important to be familiar with your specific code.
For more information about airside economizers, check out the E&L we developed a few years ago. There's a link to it in your bibliography. Next up, Susanna is going to discuss Waterside Economizer design and control.
This section builds on information provided in 2 engineers' newsletters. They are also included in your bibliography. I'll start with the most common question we get, how to control waterside economizers, which are sometimes called waterside free cooling. It's dependent on a lot of factors, so we'll go through an example. Then I'll discuss some of the pitfalls we see when trying to continue the free cooling cycle too long. Following that, I'll show an example calculation for how to meet the higher efficiency exceptions using air-cooled and water-cooled chillers. So what is a water or waterside economizer? This is the definition that ASHRAE uses. A system by which the supply air of a cooling system is cooled indirectly with a fluid that is itself cooled by heat or mass transfer to the environment without the use of mechanical cooling. In water-cooled systems, this often looks like a heat exchanger with cooling tower water on one side and system return water or return air on the other side. In an air-cooled chiller, it's likely a fluid cooler in series with the chiller or water coils nested within the condenser coils. So what else does 90.1 say about their design? All versions of 90.1 state that waterside economizers need to be capable of handling the entire cooling load when outdoor air temperatures are 50 degrees dry bulb and 45 degrees wet bulb and below. This is different than for airside economizers, which are sized to be able to bring in the full design airflow rate on the peak day as outdoor air. Waterside economizers only have to meet the load that the building is expected to need at the 50 dry bulb, 45 wet bulb condition. We'll get into later how we might go about figuring that out. Now, the 2010 and later versions add 3 new exceptions, 2 of which address computer rooms. If the system cannot satisfy the dehumidification load at 50-45, the system must meet the expected load at 45 dry bulb, 40 wet bulb. Now, the 2013 and 2016 versions are identical in practice for comfort cooling. In 2016, the word water was changed to fluid to broaden the intent to include systems with refrigerant or glycol instead of water. Also in 2016 is a new table of design temperatures for computer rooms. All 4 versions have a maximum pressure drop requirement for the heat exchangers that are used. They require the hydronic pressure drop to not exceed 15 feet of water. If this cannot be achieved, the standard requires a secondary loop to isolate the water economizer system from the chilled water loop. Now let's move on to why you would put in a waterside rather than an airside economizer. Now, it's generally agreed that airside economizers save more energy than water economizers. Dustin, could you help us understand some of the reasons why an airside economizer isn't an option?
Well, Susanna, the reasons could be the type of system, duct size or building limitations, proximity of the main air handler to a suitable location for outdoor air, or the quality of the outdoor air and our ability to clean it adequately. But in the case of hospitals, museums, or other special purpose buildings, we are often looking at humidity requirements. That is, the impact that bringing in too much outdoor air has on our humidification loads when the air outside is cooler and drier. For these reasons, hospitals in some climates are directed to consider a waterside economizer. It's even a 90.1 requirement to use waterside economizing when 75% or more of the areas are controlled to a 35-degree or higher dew point.
Let's talk next about what's at stake if we don't put in an airside economizer. Potential economizer hours are found in virtually all climate zones and in most types of buildings. From a 2016 program on airside economizers, this graph shows the hours available for economizing by climate zone and control method. This is what we are giving up, so to speak, if we don't or can't use an airside economizer. For the moist climates, anywhere from 15% to up to 50% of the cooling hours. Dry and marine climates have even more potential for airside economizing. Upwards of 40% of the hours are candidates. In most of the climate zones, there is a potential for a lot of hours where the occupied spaces can be cooled with partial or no compressor use. Now recall that starting in the 2010 version of 90.1, climates 2A, 3A, and 4A are now required to economize. To figure out our potential waterside economizer hours, we need to look at our loads plotted against wet bulb temperature. Here we have 4 hospital profiles in climates 2A through 5A. The black line is the load in ton hours. Note that the ton-hour axes are less granular in 2A and 3A, so we can show the economizer hours versus the whole year. I'll show a summary later. The area under the black curve is the number of ton hours. We are interested in the ton hours below 45 wet bulb, the point where the energy code requires us to handle the expected load, and the wet bulb when it's likely we can create cold enough water without mechanical cooling. The shaded areas, ton hours suitable for economizing in offices, are typically much smaller. I'm showing hospitals, which have at least 3 things that impact the design and energy savings potential of economizers. In favor of airside economizers are a high number of hours of operation and a high amount of ventilation from outdoor air. Due to this added ventilation, there is a natural airside economizing effect when the outdoor temperatures are favorable. And because the system isn't off at night, you get the cool nighttime hours too. All of these are balanced against humidification requirements, which sometimes means you would have to use a waterside economizer or one of the exceptions. Let's look closer at one of them. Here is the hospital in climate 4A. The area under the load curve with 45 wet bulb or lower is shaded in green. Sometimes people ask if you can have both an air and a water economizer. This orange line is the load with an airside economizer. If we were to have both airside and waterside economizers on this hospital, it would only be for the areas below 45 wet bulb under the airside economizer curve. There just isn't much there in this example. However, if we don't have an airside economizer, especially for the humidified zones, We have the green area under the blue curve below 45 wet bulb to shed with a Waterside Economizer. Now, if we don't have the ability to bring in more outdoor air when it's cool outside, we really should be doing Waterside Economizing or one of the other options I'll get into later. Here is a summary of the plant hours and ton hours that could be displaced by economizers in climate zones 1A through 5A. The colder you get, the higher the fraction of plant operating hours to be displaced by Waterside Economizer mode. The operating hours are fewer for offices, so the benefits are lower, but we do still see a benefit to the cycle, especially in the cooler climates. So now that we know why, let's talk about how. First, we have to decide on the configuration. Do we want the economizer in parallel or in series with the chillers? Now, there's language in the energy codes that requires integrated economizers. That essentially means the first stage of mechanical cooling will occur simultaneously with the water economizer cycle. For this reason, a series arrangement of the free cooling heat exchanger and the mechanical cooling device is typically used. This makes it easier to decide to initiate free cooling. The chillers will stay on until the load is fully handled. It also makes it easier to preferentially load the economizer because it sees the load first. It's also easier to accommodate the integrated economizer mode. Whatever load the economizer can't do is passed to the mechanical cooling equipment. We'll come back to that. Parallel arrangements of mechanical cooling and economizers are also acceptable, both in practice and in the energy code. In the integrated mode, the water economizer would simply mix the cold water it created with water from the mechanical cooling device to serve the load. Controls for parallel configurations can be either easier or more difficult, depending on how long you want to continue the integrated mode. From an energy standpoint, as I'm about to show, you might not lose much energy by stopping the economizer cycle once or soon after mechanical cooling is enabled. We talked already about the code requirements for sizing the free cooling device. For most applications, we need to find the expected load at 50 dry bulb, 45 wet bulb. I interpret this to mean the maximum expected load at 50-45. This is not that easy. Loads are not solely a function of outdoor air temperatures. One way I've done it is by extracting hourly loads and outdoor temperatures from an energy model. Here's that same 4A hospital with the hourly results translated into a pivot table. The rows are the percent load, and the columns are the wet bulb temperature. I'm showing wet bulb temperatures between 27 and 50. Now, the data in the intersections of load and wet bulb are the number of hours with that combination. So I'm looking for the expected load at 45 wet bulb in this chart, anywhere from 15 to 30%. The circled cell is the design condition for meeting ASHRAE 90.1, the expected load at 50 dry bulb and 45 wet bulb temperature. I found that all of the 30% load hours occurred when it was warmer than 50 dry bulb. So that's how you might figure out the expected load at 50 dry bulb and 45 wet bulb. In this case, we're looking to provide 25% of the design cooling load with a Waterside Economizer at 50-45. The next step is to figure out how the tower will perform there. To do that, we have to determine how the cycle is controlled.
Given the high number of variables at play when deciding how to control the Waterside Economizer cycle, it's difficult to come up with a package control algorithm. We have to modify it based upon the application. As with other chilled water system complexities, air-cooled equipment has knowledge and control of many of these variables. When we have an air-cooled chiller with a Waterside Economizer installed on board, system controls are typically built in. But for water-cooled systems, this coordination happens in the system controller and be informed by things such as the load, the wet bulb temperature, the number and type of chillers, and the number, type, and flow turn-down characteristics of the cooling tower and heat exchanger.
So now we have to figure out how the cooling tower will perform in the likely uncertified region of its performance predictions. If we bring back up that hourly data, we can see that there are some combinations that didn't exist in the model. For each column at a given wet bulb temperature, the lowest row with hours in it is the highest load expected for that wet bulb temperature. Working with a cooling tower provider, we can find the leaving temperature we can expect the cooling tower to generate. In this particular example, I assume that we have 3 chillers and 3 tower cells. If our tower has sufficient flow turn down, we can spread the flow over more tower cells and slow the fan speed down as low as possible. 90.1 requires a 50% flow turn down, so we should pick a heat exchanger that can handle the minimum flow of 2 tower cells. I'm going to use a tool that we have for predicting cooling tower performance. On a real job, you would get this from the tower provider, but since this is a hypothetical case, I'm going to use a different method. The result of the exercise I'm about to show you gives us some potential control points. At the far left, in the coldest wet bulbs, we only need 1 cell running. From 34 to 45 wet bulb, we have 2 cells operating, and above 45 wet bulb, we have all 3 tower cells operating. Let's look into how we got there. In the coldest operating mode, we run 1 cooling tower cell to a 47.5 degree set point. How did we pick that temperature? For this application, it was decided that 50 is the warmest chilled water temperature we want to provide to the system, and a plate and frame heat exchanger has about a 2 to 3 degree approach. We also need to pay attention to the energy consumption and make sure that the tower fan is no higher than 100% speed. Because we have a heat exchanger, we also include a dedicated pump for it on the evaporator side. For the coldest regime, the combined efficiency, the tower, condenser, and free cooling water pumps, is 0.079 kW per ton, and the fan speed is 33%. As the wet bulb climbs, we need to add another tower cell. The second column is 39 degree wet bulb and still at 20% load. We've added a second cell so the tower fan speed goes down. The farthest right combination of load and wet bulb is where we can no longer maintain 47 degree leaving water from the tower because the tower fan exceeds 100%. We would have to turn on a chiller. Because the fan energy starts to really climb, the cycle has an efficiency of 0.55 kW per ton. This information is important to know because it helps us decide when we can and should stop using the free cooling cycle. More on this in a few moments. The result of this is the first estimation of some control points, the tower set point, 47, and the wet bulb temperatures when we're likely to need to add a tower cell, 39, and when to start the chiller, 45. We will also add a condenser pump and a tower cell when the chiller comes on. Now you might be surprised by the efficiency in the final 2 columns. In order to figure out when to add a cell, when to add a chiller, and when to discontinue the Waterside Economizer mode altogether, we ought to know the efficiency. If we refer back to this diagram, we can see the cooling tower with its circulating fans, the condenser water pump, and the free cooling pump. The part that's not shown is the chilled water pumps and the supply fans. When we are Waterside economizing, the chilled water pumps may have to work harder because they're distributing warmer chilled water. Also, the supply fans in turn might be at a higher speed because the system may be using warmer chilled water at the end of the cycle. So let's talk about the end of the cycle. At the end of the free cooling cycle, we enter integrated mode. We start a chiller, and so we have a blend of free cooling and mechanical cooling. This is the most tenuous portion of the controls, as you'll see. What I mean is the value can be great or can be lousy. This matters because it helps us figure out when to stop free cooling. Here you see a graph of efficiency of the system as a function of load. The 2 curves are the total system efficiency at the minimum and maximum cooling tower fan power. While it's tempting to assume that all of the operating points will fall between these 2 extremes, we can also see quite a number of points when the minimum fan power was achieved, yet the efficiency was far worse than expected. The most disturbing thing this graph reveals is that even at minimum fan power, there comes a time when the efficiency of free cooling is horrible, 2 kW per ton. Why is that? For one thing, the tons are too low for kW per ton to look very good. Also, we don't have wet bulb on this graph because it's only 2 dimensions. Let's look at efficiency as a function of wet bulb instead. We'll have to hold load constant in order to do that. Here you can see one load condition. We fixed it at 50 tons of load and isolated the effect of trying to get to a specific leaving water temperature on the energy use by the tower fan. The blue line is fan power at 500 GPM of water flow. As our wet bulb climbs, but the load remains constant, the fan power goes up dramatically following our fan affinity laws. The tower approach is low. The tower, after all, is still trying to achieve set point, but fan energy is not. Operation in that region should only be used as a last resort. The optimal control range stops before we see a large spike in the fan power. 50 wet bulbs seems like a good maximum wet bulb for integrated free cooling mode in this example. The story doesn't end at the tower fan. In integrated mode, the chiller is also operating at a relatively inefficient point. There are too many tons being stolen from the chiller, and it moves to the left on the performance curve. This is true no matter what kind of chiller you have, even one with magnetic bearings. The condenser pressures are as low as possible, but the kW per ton is quite high. There are simply not enough tons to spread out the relatively low kW over. Said a different way, when a chiller is running, there is a minimum kW that it needs, regardless of load. The controls, any ancillary power use, and the minimum compressor energy. When loads go down, even the best performing cold weather chillers have worse efficiency than might be hoped for. One suggestion is to give the chiller more load and the Waterside Economizer device less. This is difficult to do in a series arrangement, but it can be done. It's easier to do in parallel Waterside Economizer arrangements. Now there is something else we can do. In the integrated mode, the chiller is most likely controlled to a minimum head pressure. That is, the condenser water has been slowed or bypassed around the chiller. When we implement chilled water reset in order to prolong the free cooling cycle, we are keeping our chiller in head pressure control mode longer than we need to. Release chilled water reset while in head pressure control mode. It wastes no energy because it allows the chiller to perform more cooling for the same energy input. That means the coils will start to perform better and our system delta T should go up, with a higher return water temperature entering the free cooling device. As supply temperatures go down, valves close and flow goes down. At the same load, coil return temperatures stay the same or go up. Our broadcast earlier this year discussed coil performance. Please check that out if you missed it. Now let's look closer at the effect releasing chilled water reset has on the chiller. The first row is a fixed speed chiller operating at 49 degrees, leaving chilled water set point, and about 64 degrees, leaving condenser water. The efficiency of a minimally compliant chiller is about 0.608 at these conditions. If chilled water reset were released to 45 degree leaving chilled water, the leaving condenser drops to 61, and the chiller actually gains a little bit of efficiency. Similarly, the variable speed chiller will create colder chilled water with the same amount of energy. A variable speed chiller is also a great idea for the first stage of mechanical cooling. Note, these values are for one point in time. They are not part load values. Bottom line, releasing chilled water reset saves energy and helps the water economizer pre-cool the water to the chiller. Now, when else should free cooling mode end? One method is when not enough pre-cooling to the chiller is happening. And as I've already discussed, it's important to know the efficiency of the mechanical cooling system when free cooling can't go it alone anymore. Once a chiller comes on, the cycle performs progressively worse, with the added heat of compression having to be rejected by the cooling tower. In summary, water-cooled free cooling is complicated, but here are some takeaways. Looking at load profile history and full-year load profiles extracted from energy models can help determine the control points. Work with a tower model or a tower manufacturer to predict which conditions are favorable for free cooling. Release chilled water reset once the chiller comes on. Chiller, tower, and pump energy estimates at the end of free cooling mode can determine your exit strategy, when to release the cooling tower to its optimized set point. And if the lead chiller is variable speed, consider terminating free cooling sooner to save tower fan and condenser pump energy. There are a few alternatives to economizers that may make more sense for your application. The first one is more efficient equipment. As Eric alluded to earlier, starting in the 2010 version of ASHRAE 90.1, designers have been given the option to choose higher efficiency cooling equipment in both the simplified and the prescriptive compliance paths. The premise is that with more efficient equipment, you can equal or better the energy benefits of the economizer. Prior to 2010, this exception only applied to applications that qualified for the simplified compliance path. For packaged equipment and chillers, it's easy enough to do the calculation. Simply look up the table value and adjust it by the efficiency corresponding to your climate zone. There already is a unitary example in the 90.1 User's Manual. Today I'll show us two additional examples for air-cooled and water-cooled chillers. The premise of the economizer trade-off table is that in warmer climates, higher efficiency equipment has more hours of operation to make the economics work. But variable speed equipment also isn't quite as big an advantage at higher ambient temperatures. So 90.1 undertook an effort to qualify how much efficiency improvement would be needed to offset the loss of the economizer cycle. In this case, the Airside Economizer cycle was used as the basis. Eric earlier showed these tables. The first one is from 90.1, and the second table is from IECC 2018. Now let's do an example for an air-cooled chiller. In 2015, the efficiency rules gained stringency, so we'll improve on those to justify our exception from economizers. In 90.1, the improvement is over the part load metric, such as IPLV, if one exists. In IECC, it's over either the full load or IPLV. Air-cooled chillers can comply using either the IECC or 90.1 compliance options. There are also two paths, A or B. You can comply using either path regardless of technology, as long as you meet both criteria. For less than 150-ton chillers, the part load requirement is 13.7 IPLV, with a full load also at or better than 10.1 EER. Let's imagine a chiller going to climate 2A. This equation shows the efficiency we would have to select in climate zone 2A in this particular class of equipment. For IECC, starting in 2018, we have two higher efficiency options. We can use either the full load or the part load improvement to comply. Here you see that a full load efficiency of 11.1 or higher would qualify for this exception in climate 2A or 2B, or an IPLV of 15.1 or higher. Now let's do another example, water-cooled centrifugals. The highest likelihood of qualifying for the efficiency exception in this category is for variable speed chillers that still meet the full load of Path A. But centrifugal chillers have a dynamic efficiency requirement. We have to first use the spreadsheet from ASHRAE to determine the requirements. Let's look at a 400-ton or larger chiller making 39-degree water with 93 degrees leaving the condenser at design. These are the orange entry fields. The minimum efficiencies are at the bottom in green, 0.6076 kW per ton at full load and 0.5425 at part load. In climate zone 3A, to eliminate the economizer requirement, the chiller must be 27% better on IPLV while still meeting full load. So at these conditions, that means a part load value of 0.3960 and a full load efficiency of 0.6076 for climate 3A. In IECC 2018, if my chiller has a full load of 0.5165 or better, or a part load value of 0.4611 or better, it would comply. Both of these situations can be accommodated by water-cooled centrifugal chillers. Other systems have another option instead of putting in either an air or a water economizer, condenser heat recovery. In southern climates, we saw eroding benefits from water economizers because of higher wet bulb temperatures. Now, these are climates that tend to benefit from condenser energy recovery due to reheat, active humidity control. The cooling season is long, and the benefits of recovered energy don't need to be as high to offset what was lost by not economizing. 90.1 allows condenser heat recovery to be used instead of economizers, provided that the size of the heat recovery system is large enough. The thresholds are shown here. 60% of the peak heat rejection load is used for service water heating, or preheating of the peak service hot water is to 85 degrees. Two other options for size are 30% of the peak heat rejection load for space heating, or 60% of the service water heating is by site solar or site recovered. Heat pump and heat recovery chillers could be used to qualify for this exception. Keep in mind that the heat rejection load is approximately 25% more than the cooling load due to compressor heat.
Thanks, Susanna. Now that we better understand both airside and waterside economizers, let's look at the economizing options available on some of the most common system types. Dustin?
There are many different system configurations, but as a first pass, we can classify them in one of two ways. The first is as a centralized system, with an example being a multiple zone variable air volume system. The second is as a distributed system, which will typically include both a terminal system and an independent ventilation system. Examples of distributed terminal systems include chilled water fan coils, water source heat pumps, and VRF. We'll cover both centralized and distributed systems in what follows. Let's start with centralized systems, which, when compared to most distributed systems, can more easily accommodate airside economizing. A centralized system includes everything needed to condition and ventilate the space. Centralized systems include package DX rooftops, commercial self-contained units, and central station air handlers. Systems with package DX rooftops contain the mechanical cooling and heat rejection in one packaged piece of equipment. Systems with commercial self-contained units or central station air handlers are connected to a chilled water plant or a remote air-cooled condenser. Note that any of these variations can be applied in a single or multiple unit setup throughout the building. For purposes of this discussion, we'll consider multiples of these units types of a centralized system. First, the package DX rooftop. These units contain an integral air-cooled condenser and don't require separate cooling or ventilating equipment. Since the package DX rooftop is already handling ventilation air, with supplied ductwork sized for the full needs of the space, it's relatively easy to accommodate airside economizing. These products will include a modulating damper and integrated control options to cool the space using outdoor air. In many cases, they may also include components for centralized building exhaust and even exhaust air energy recovery. As these systems are totally self-contained, without any form of water loop, waterside economizing isn't typically considered. Another centralized system type is a commercial self-contained unit, also known as a floor-by-floor unit. These products are available in two options, one that uses a remote air-cooled condenser and one that uses a water loop. In the case of the former, an airside economizer is an option. In the case of the one that uses a water loop, a waterside economizer is an option. In this case, a separate water coil is added in series with the primary DX coil to enable waterside economizing, similar to a water source heat pump, which we'll discuss later. Although an airside economizer is available with a water-cooled unit, one will generally choose either airside or waterside economizing. Our final centralized system consists of central station air handlers that can use a chilled water coil or a DX coil to cool the air. The coils contained within the air handlers will be connected to a chilled water plant or a remote air-cooled condenser in the cases of a DX coil. Similar to a packaged rooftop unit, a central station air handler is already handling ventilation air with supplied ductwork size for the full needs of the space. In the case of an outdoor air handler, it's relatively easy to accommodate airside economizing, same as the packaged DX rooftop unit. In the case of an indoor unit, however, the upstream ductwork would have to be upsized beyond minimum ventilation requirements to enable full airside economizing. Although airside economizing is generally the most efficient choice, we pointed out a number of reasons why a waterside economizer might be needed. Luckily, a chilled water air handler can easily accommodate waterside economizing. In these cases, the same water coil is used, so there's no change in airside pressure drop. While a separate water coil could be added to a DX air handler, it's unlikely there's a water loop in the building. If a separate coil is indeed added, there would be a corresponding increase in airside pressure drop. Next, let's look at distributed systems. Instead of a central chiller plant or condensing unit, a distributed system distributes much of the mechanical cooling throughout the building. In most cases, this means that there will need to be two separate systems, a system to handle the ventilation needs of the building and a separate terminal system to handle the individual needs of the space. The ventilation system could use a simple energy recovery ventilator or a dedicated outdoor air unit. The primary difference between the two is that a dedicated outdoor air unit includes mechanical cooling, and it can be designed to handle the dehumidification load in part or in full, the latter resulting in a sensible-only terminal system. The mechanical cooling in a dedicated outdoor air unit can be packaged or split DX, or hydronic for those terminal systems that use water. Although there are a few exceptions, most distributed systems will be coupled with a separate ventilation system, so we'll start there. Then we will walk through the economizer capabilities and requirements for some of the most common terminal systems. The term economizer, or more specifically, the term air economizer, can get quite confusing when discussing distributed systems, ones with a separate ventilation system in particular. So let's make for sure we fully understand what that word means in the context of distributed systems. The term air economizer is defined in ASHRAE 90.1 as a device that can reduce or eliminate the need for mechanical cooling. In the case of a distributed system, where there may be two airflow paths to the space, this definition alone doesn't distinguish which airstream the economizer applies to. For example, if the ventilation system includes an economizer function, does that mean that the building has an air economizer in the traditional sense? The standard provides a partial answer to this question in the section on air economizer requirements. Specifically, the requirements mention both outdoor air and return air dampers. That seems to imply a mixed air system, not an independent ventilation system. Likewise, the requirements state that the system must be able to provide up to 100% of the design supply air quantity, an amount not typically provided with an independent ventilation system. So an air economizer is effectively a full economizer, with a classic example being a centralized multiple zone VAV system. However, a ventilation system that has been sized to provide up to 100% of the design supply air quantity with mixed air capabilities could also meet this intent. To reduce confusion, we can use the qualifier ventilation to better describe the economizing capabilities of a building with a separate ventilation system. So a centralized system will be considered an air economizer. However, a ventilation system with a dedicated outdoor air unit that can disable mechanical cooling during mild or cold weather would be considered a ventilation air economizer.
To be clear, ventilation economizer is not a term that's defined in ASHRAE Standard 90.1, and this type of economizer would not meet the requirements of Section 6.5. However, the use of this qualifier should help to reduce confusion in the industry.
Correct. So a ventilation air economizer is effectively a partial economizer, as it is sized for the ventilation air requirements and not 100% of the design supply air quantity. In the event the ventilation system is sized for 100% of the design supply air quantity, the system would meet the requirements for an air economizer and should be referred to as such. Note that more airflow could be brought in, but such an economizer would still be a partial economizer if less than 100% of the design supply air quantity. So in terms of options, a ventilation system is unlikely to have a full air economizer as prescribed in ASHRAE 90.1, as it would be difficult to provide full economizing capability while keeping static pressures in check. Only if the duct system was designed for a much higher airflow would this work. However, a ventilation system can have a ventilation air economizer, and as mentioned previously, some dedicated outdoor air systems are hydronic, which means waterside economizing could be an option. This may be useful, for example, in an application where humidification is needed. Now that we've covered the ventilation system in detail, let's discuss economizing options and some unique code or standard requirements associated with a variety of terminal systems. The choice of terminal system varies widely, but we'll cover some of the more common systems in what follows. Here we'll discuss a few fan coil variations, some systems that are capable of heat recovery, sensible-only terminal systems, as well as some compressor bearing systems. So our first terminal system to discuss is a common fan coil. As its name implies, it consists of a chilled water coil and a fan at a minimum. These units primarily draw return air from the zone and pass them through the coil. The air is then discharged directly to the zone or to a duct that's connected to one or more diffusers. Note that fan coils can include DX coils in lieu of a chilled water coil. DX fan coils can be part of a VRS system, which we will cover later, or independent split systems. Ventilation in a fan coil system is typically handled by a separate ventilation system. But some fan coils are offered with a fresh air damper option, which could enable some level of airside economizing. Higher static fan coils, sometimes called blower coils, often have a mixing box option, which could enable full airside economizing. And if the fan coil uses a chilled water coil, waterside economizing is also an option. A variation of the fan coil is the unit ventilator, most commonly applied in classrooms. In addition to a more durable cabinet, a unit ventilator includes an outdoor air intake that's sized to enable full airside economizing. That is, an air economizer as described in ASHRAE Standard 9.1. This is one of the primary advantages of a unit ventilator. It easily enables full airside economizing. Note that if the unit ventilator is hydronic, the same coil could be used for waterside economizing. A related variation of the fan coil is a sensible cooling terminal unit. In this case, conditioned air from a dedicated outdoor air unit is ducted directly to the terminal unit via an airflow measuring damper. This outside air is intentionally delivered at a low dew point, 47 degrees Fahrenheit for example, to sufficiently dehumidify the building. That is, the dedicated outdoor air system is designed to handle the full latent load of the space. The remainder of the unit functions somewhat similar to a fan coil, with one notable layout difference. The coil is in parallel with the conditioned outdoor air path. This arrangement provides independent control of the recirculated air to handle the remaining sensible load of the space. And since the coil is sensible only, water in a hydronic system can be delivered warmer than would be the case in a system that combines both sensible and latent cooling, with 56 to 60 degree water temperatures being typical. Similar to a chilled water fan coil, waterside economizing can be achieved in a sensible cooling terminal unit without the need for a second coil. But with a warmer water temperature, we can expect a substantial increase in the number of hours when economizing is available. This chart plots the annual cooling load for an example building located in Climate Zone 4A. The outdoor ambient temperature is plotted on the horizontal axis, and the percent of design cooling load is plotted on the vertical axis. As expected, the unit is operating at full load on a hot summer day and operating close to no load on a cold winter day. But note how the building still needs almost 70% design load between 45 and 50 degrees outdoor ambient, a range important to meet the ASHRAE requirements for a waterside economizer. Here we've updated the plot to show when water economizing is active, taking into account the warmer water temperature. For this example building, we can see that the economizer is not only able to meet the ASHRAE requirements, it can handle about 25% of the annual cooling load and 35% of the annual cooling hours. Now this example utilized a water-cooled chiller system where the cooling tower could be used for waterside economizing. With an air-cooled chiller, consider a model with integral free cooling, or consider adding a dry cooler just for use during economizer operation. So our next terminal system involves water source heat pumps. With these systems, each zone has a unit that is connected to a common water loop controlled to maintain the desired temperature in that zone. The water loop includes a heat rejector, like a cooling tower, and a heat adder, like a boiler. Alternatively, the heat rejector and/or the heat adder could be a geothermal heat exchanger. Water source heat pumps come in a variety of configurations, including horizontal, vertical stack, or even rooftop. Similar to a packaged rooftop unit, a rooftop water source heat pump can easily accommodate an airside economizer. On the other hand, interior water source heat pump units have a waterside economizer option. Economizing is enabled with a separate coil in series with the DX coil. A two-position, three-way valve chooses whether the cooling tower water goes to the free cooling coil or to the heat rejection coil. Variable refrigerant flow, or VRF, is our next terminal system. A VRF system is typically an all-variable speed, one-to-many split system with an option for heat recovery between zones. VRF systems utilize a number of terminal unit options, including ceiling cassettes, high wall units, and fan coils. A VRF system is typically air source, but a water source option is also available. Water source systems are especially useful in ground source applications or for climates dominated by heating loads. In general, airside economizing is very difficult to implement with a VRF system. However, it's important to note that an economizer is generally not required by codes and standards due to a number of exceptions that apply to VRF systems. As we discussed earlier, the individual fan cooling units will likely fall below the 54,000 BTU per hour threshold. Keep in mind that this threshold applies to the individual terminal units, not to the total capacity of the outdoor VRF unit. However, unlike some other terminal systems that utilize compressor bearing equipment, VRF systems with all variable speed components should be able to meet the part load efficiency exception in many climate zones. With that being said, there is one VRF terminal unit option that can meet an Airside Economizer requirement, a unit ventilator equipped with a VRF coil. As mentioned earlier, a unit ventilator is a special type of fan coil with an outdoor air intake that's sized to enable full Airside economizing. The next type of terminal system involves the use of chilled beams. This system distributes chilled water to a network of beams above the space that cool using convection. They are available in two configurations: a passive configuration that cools the space without the use of any fan, and an active configuration that contains an integral air supply from a central air handling unit. The integral air supply in an active configuration serves to induce air from the space to substantially increase cooling capacity and provide ventilation. A variation of the chilled beam is a radiant panel. These devices also distribute chilled water, but they are limited to the radiant mode of heat transfer. To prevent condensation in the space, chilled beams and radiant panels are sensible only with a higher water temperature, similar to the sensible cooling terminal unit system discussed earlier. And as we discussed earlier, IECC has an economizer requirement for chilled water systems with system capacities above a certain threshold. This would include chilled beams and radiant panels. ASHRAE 90.1 2016, however, contains an exception for systems without a fan or that use induced airflow, below a certain system capacity threshold. This qualification would include both passive and active chilled beams, as well as radiant panels. Above that threshold, a water economizer should be used. And as was discussed earlier when we covered sensible cooling terminal units, sensible systems use a warmer water temperature, so waterside economizing hours are increased when compared to a chilled water system with a lower water temperature. The final terminal system that we'll discuss today is the common packaged terminal air conditioner, or PTAC for short. These units are typically used in hotel rooms or other single-room dwelling units. PTAC units don't really have an economizer option. They do, however, include a small, non-modulating vent door. In fan-only mode, I suppose the unit could provide some level of economizing capability, but the capacity certainly can't be controlled, a requirement for codes and standards. However, PTAC units will generally be exempt from economizer requirements. That's because their size will generally fall well under the 54,000 BTU per hour threshold. Okay, we've covered a lot of terminal systems today, so let's briefly summarize the requirement thresholds and economizer options for each. As we can see, most of the chilled water terminal systems have a system capacity requirement, but there are waterside economizer options for each of these. We can also see that small DX equipment, VRF and PTACs in particular, have limited to no economizing options, but they also benefit from the fan cooling unit size or part load efficiency exceptions to the requirement for an economizer.
Thanks, guys. We hope you enjoyed the C&L program and that you found it helpful. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic. Or contact your local Trane account manager for specific information on Trane systems and controls. And be sure to subscribe to the Trane Engineers newsletter. For those of you seeking continuing education credit, be sure to check out our continuing education programs, which include many past E&Ls, including a program focusing on Airside Economizers, all free and on demand. And remember to fill out a survey and let us know what you thought of today's program. And AIA members, please turn in your member information to your local site coordinator. And finally, ask your local host about details for the next Engineers Newsletter Live program and the lineup for 2020. Thanks for your time today. We look forward to seeing you next time.